Welcome back to this video on the topic of indices. In this video, we're going to have a look at something called scientific notation. Now, scientific notation is a means of representing either very large or very small, or we could say extreme numbers, in a form that's easier to read and process. So to write a number in its scientific notation form, we usually write it as a times 10 to the power of k, where a is a number that's between the numbers 1 and 10. However, it can't equal the number 10, so it's between 1 and 10. And the value of k is an integer number. So it's a whole number, but it can be both positive or negative. Okay, so now that we've got this concept out of the way, let's have a look at how we can convert some quantities from the standard notation, so the notation we usually look at, to scientific notation. So if we go down, we've got 5 different examples here, and we want to represent these quantities using scientific notation. So part A, 27, we want to write this using scientific notation. So what we want to find is we want to have the number a, which is going to be between 1 and 10, and we want to multiply it by 10 times something, or 10 to the power of something. So first thing we need to think of is how can we modify 27 to be between 1 and 10? And the way we can do that is we can rewrite 27 as 2.7. So now it's between 1 and 10. But if we're changing the value of this number here, then we also need to multiply it by something. So times 10 to the something. Now, to know what the exponent's going to be, we first identify the decimal point on the original number. So originally it was here. And what we did was we moved it over to here. So it did a single hop of 1. So the exponent on our 10 is going to be, it will be times 10 to the power of 1. So what we've done is we've changed 27 to scientific notation by rewriting it as 2.7 times 10 to the 1. Now, example B, we have 580, and we want to rewrite this using scientific notation. So once again, I'm going to write out the number 580. And because we need A to be between 1 and 10, we simply put a decimal point between the 5 and the 8. Now, to compensate, we have to multiply this by something, so it will be times 10 to the something. Now, to calculate what we're timesing it by, a decimal point was originally here, and we moved up 1, 2. So 1, 2 places. So we're going to get an exponent on this 10 as 2. So the scientific notation form is going to be 5.8 times 10 to the 2. And another way we can rewrite this is we can drop the 0 or the 0 here altogether because it doesn't actually have any place value. So it becomes 5.8 times 10 to the 2. Or you can leave the 0 in. It's up to you. Now the second one, 3040, we want to rewrite this using scientific notation. So I'm going to rewrite the number out again, 3040. And the decimal point is going to move just after the 3. So pretty much there's always going to be a single digit in front of the decimal point. Then because I've changed that, I need to multiply it by something. Now looking at this, we moved the decimal place. It was here and it went 1, 2, 3. So the exponent on our times 10 is going to be 3. So we represent 3040 as 3.040 times 10 to the 3, or in this case I'm actually going to drop the 0, and it will be 3.04 times 10 to the power of 3. There we go. Alright, next example D, we have 0.75. Rewriting this using scientific notation, we go 0.75, we drop the 0 in front and we just write 7.5. And then we put a point between the 7 and the 5. After that, we have to multiply it by 10 because that's our form. Now this one's different from the first three in that rather than moving the decimal place to the left, we're moving it to the right, and we're moving it to the right by one space. So it's going to be times 10 to the 1, but it's going to be minus 1. So what you're going to find is that when you move the decimal place to the left, you get a positive exponent, and when you move it to the right, you get a negative exponent. Now, final example, 0.0034. Rewriting this using scientific notation, we write 3, 4, dropping all of the leading zeros, and we simply move our decimal place between the 3 and the 4. Then we go times 10 to the something. Now I have to go back and count. Our decimal place is here, and we move it 1, 2, 3. 3 spaces, so we put times 10 to the 3, and it moved to the right, so it became a minus. So, when moving the decimal place to the left, the exponent is positive. In contrast, when moving the decimal place to the right, the exponent is negative. Similarly, if we describe the notation or the form on the right-hand side of the equal sign over here as scientific notation, then conversely, the form of the numbers shown on the left-hand side, we call that standard notation. So the opposite of scientific notation is called standard notation. Alright, so now that we've got our abilities to convert to scientific notation out of the way, let's have a look at how we can convert scientific notation back to standard notation. So moving down in example 2 here, we've got A, B, C, D, and E, where all of our figures here are represented in scientific notation, and we want to be able to convert these back into their standard notation form. So to be able to do this, it's simply a matter of we get 3.2 and we multiply it by 10 to the power of 3. So what this infers is that we write 3, 2, and our decimal place was over here. And what we're going to do is we're going to move it 1, 2, 3 spaces to the right. So we'll go 3, 2, 0, 0. So if we don't have anything or if we run out of usable digits, we can just stick zeros behind it. And what we find is that 3.2 times 10 to the 3 is the same as writing 3,200. Now going down to example B here, we've got 5.8 times 10 to the 8. We're going to convert this back to standard notation using the same method. We simply write out the digits that we have. So in our case, we've got 5 and 8. Now we need to figure out how many zeros we need to add in. So it's times 10 to the 8. The decimal point was over here originally. So that means we're going to move it back 1, 2, 3, 4, 5, 6, 7, 8. Putting this figure down, we add zeros. So what you end up finding is that the number becomes, let's have a look, so it will become 580 million. So 1, 2, 3, 4, 5, 6, 7, 7, 8. So 580 million. So quite a large number, much easier to read when it's in this scientific notation form here. Alright, now C. We've got 4.9 times 10 to the 3. 10 to the negative 3, I should say. So once again, we're going to solve it using we're going to convert it using a similar method, but because our decimal place is going to be moving to the left because we're dealing with a negative exponent here, I'm going to leave a little space in front. So I'll write 4, 9 like so. And our decimal place was originally over here, but it's going to move 1, 2, 3 spaces to the left. So our decimal place will show up here. So because of that, we have to put some zeros in, and then we should stick a 0 in front for good measure here. So what we find is that we've moved it 1, 2, 3. So therefore, the standard notation form of 4.9 times 10 to the negative 3 is 0.0049. Alright, D. This is where working in scientific notation is really helpful. We've got 2.0 times 10 to the 4 times 3.4 times 10 to the 2. Two rather different numbers, differing in magnitude, but because we can use scientific notation and subsequently our index laws, we're able to crunch these sort of numbers rather quickly and effortlessly. What I'm going to do is I'm going to multiply the two A components of these scientific notation forms, so 2.0 times 3.4. That's going to give us 6.8. Now, we have to deal with the exponents here. So I've got times 10, and it's a common base. So because of its common base, we're able to add the two exponents together. So it becomes 4 plus 6. Going down, this will simplify to 6.8 times 10 to the power of 6. And I'll just get some more space. We'll do. And rewriting this in standard notation form, we write out 6, 8, and we're going to move, actually I'll use the grids, 6, 8. Our decimal place was over here, and we're going to move it 6 places to the right. So we're going to go 1, 2, 3, 4, 5, 6. So putting a 0 in all of those free spaces, what we find is 2.0 times 10 to the 4 times 3.4 times 10 to the 2 is equal to, that's thousands, millions, 6,800,000, or you can simply write it as 6.8 million. So what would usually cause us a little bit of grief and make us want to go for the calculators, we find that we can do these in our head quite easily now. In our final example, we have 1.5 times 10 to the 7 times 8.0 times 10 to the negative 5. Computing this, we're going to multiply 1.5 and 8 together. So that's simply 8 plus half of 8. That's going to be 12 times 10 to the power of 7 times 10 to the negative 5. The common base of 10, we add the exponents together. So we go 10 to the 7, take 5. So we're adding, I'll rewrite that. We're adding negative 5 to 7. So that will become 12 times 10 to the power of 2. And then we simply rewrite it as 12. And we're going to move our decimal place back. It was here, it's going to go 1, 2. So the resultant value is 1,200. So this has been a video showing you how, firstly, you can convert numbers using scientific notation, or how you can represent quantities using scientific notation as seen in example 1. And then secondly, we learned how to go the reverse way, so how to convert numbers that are in scientific notation back into their standard notation form.